As said, I'm Oliver Bratton, Director, Network Strategy and Operations. And I'm just going to tell you a bit about what I do and the work I do. And I'm hoping, and someone will confirm shortly, that you can see my screen. Is that the case?
Yeah, that's working.
Right. So who am I? As I said, Oliver Bratton. I've done 23 years in the railway, and much of my job is how we get most from the Great Britain rail system. And there's a lot of decisions to be made around that, you know, how reliably the system runs, how many vehicles we run, and journey time for passengers and freight users all have to be weighed up against each other. And you're probably aware that the more things you have on a system, the more congested it gets. So the M25 around London tends to be quite slow, whereas in other parts of the country, the motorways are quite fast, where there are fewer vehicles. And the same goes for the railway. The more things you put together, the more congestion you get. And the question is how you balance those, given the fact that passengers want fast journey times, they want comfortable journeys, but they also have to balance cost, and cost is a big issue for the railway because it's a very expensive system. And that's why I put at the bottom, how do you price the railway? Because everything that you see around you, all those trains moving around, the track, the staff, it all costs money. And somehow you've got to understand how it all costs when you're balancing your equation. So I'm going to just go through some of the things that I work on in my day-to-day job and show you how important data and statistics are to the work I do. And I think it's important to say that, you know, however clever what I do may sound at times, a lot of it's very basic. So anybody who's done the very basic equation of speed equals distance over time is actually, that's a key part of my job. You know, that one equation drives a lot of the work I do. Just show you some of the variety of the work I'm involved in, and particularly around weather, because weather has a really important role to play on the railway for a number of reasons, and I'll go on to that when we get there. But I'm going to start with a question for you just to think about as we go through the presentation. So when you see all those trains moving around the system and all those passenger carriages, if you put one end in London at the bottom of that map and coupled them all together, where would the front be? Well, how long would that train be if you put every single vehicle together? So I'll come on to that at the end. So that's your incentive to stay with me right through to the end of the presentation. So just to explain something as well before we start, the railways don't have traffic lights. We have signals instead. And that's quite important because when you're trying to understand how it works, and this is what a lot of my work is involved in, you just have to understand some of the basic operating principles. And in a train, because trains move so fast, you can't sort of just show a driver a green and then suddenly put a red in front of them. You have to show them a sequence of signals that they slow down. So this diagram here just gives you an idea of how that works. The green signal tells a driver that the line's clear ahead. The double yellow tells them to prepare to start slowing down. The yellow signal shows them that the next signal is going to be red, and then you stop at the red signal. On the railway, when trains are moving up to 125 miles an hour, the distances between these can be quite large. Otherwise, trains would find it very difficult to stop. But as I say, this is important because the way it works isn't quite like the road system. But what it also means is that the more restrictive aspects, the double yellow and yellows you see, the slower the system goes. And understanding that balance is one of the key parts of my job. I'm going to show you now what might look quite complex, but it's actually quite simple. So this is a timetable as shown in a graph form. And along the top, you see the time of the day. So it starts at 2 o'clock in the afternoon, 1400, and then every 5 minutes is a little marker on the top. And then down the side, you get the codes of the station. Now, this is a timetable that's not yet running. It's actually going to be the Elizabeth line in London. So the tunnels under London have been built over the last few years, haven't started running yet. But this shows you how a timetable looks from Paddington through to Stepney Green Junction. But this is how we represent the movements of trains. As I said to you, this is actually a very basic graph because I'm sure all of you have done some level of graphs. Yet it's a key part of what I do. How do you space those lines in order that you get the best possible service? How do you optimize the gradients so that you get the best possible journey time? And how do you avoid interactions because of the way that signaling works so that one train affects another? The different colors represent different cooling patterns outside of the tunnel section, because for those of you who might know London, the tunnels between Paddington and Whitechapel. At the end of those, the trains go to different destinations in the southeast and West London. So the colours are a way of representing different layers of data across the core point. But in that, you'll see a number of things about how, you know, computers, in fact, need to be coded in order that you can put data in. You know, it's very, we don't type out full names of stations and things such as computers, because things like spaces cause errors. So we make sure that we keep we code station names rather than putting their full names in. So you'll see Westbourne Park at the top, Paddington Low Level, Bond Street, Tottenham Court Road, Farringdon, Liverpool Street, and then going through Whitechapel and Stepney Green Junction. But as I said, this graph, however basic, is absolutely key to what we do on the rail system to describe the occupation of the network by trains. And just to remind ourselves, this is what we're talking about: very large lumps of metal, very, very expensive things. How we move enough of these around to move the maximum number of passengers. On a normal weekday before COVID, the UK rail system was moving around 4.5 million people every day. And you can imagine that that requires a lot of vehicles. So here's a question for you. We're saying that a red signal is there to protect a train. The faster a train goes, the shorter that time the signal will be red. But that can be affected by how slowly the train goes, if the train is longer, and if the train enters on one of those signal aspects other than a green. So when you're planning that set of lines, you're making some assumptions as to how the train will move through the system. If the train goes more slowly, the signals will be red for longer. If the train is longer, the signal will be red for longer. If the train doesn't enter at the fastest possible speed, which is the green, you start seeing the signal staying red for longer as well. So one of our challenges is how we ensure that where possible, trains see green signals, which really ensures about keeping them separate. And that's very difficult on a very congested urban network. As I say, it's like trying to keep the M25 flowing at 70 miles an hour. We know we should be able to, but it's very, very difficult. And therefore, a lot of my work is around measuring if the system is performing as it should do, and then trying to understand the causes of why we get disruption on the network. And the causes of disruptions, you probably know that there are lots of reasons. They might be that there might be a fault with the infrastructure, there might be a fault with the train, it might be the fact that we've got a problem at a station and the train can't depart because there's too many people getting on, or maybe a passenger's had an accident and we've had to hold the service while we deal with that accident. The point is that all of these things are making sure that we can't run the timetable as best we can. And therefore, my job is to try and see, can we improve the way we run the railway? Can we keep that system flowing? Can we keep the drivers seeing green signals? I put this up just to show how we run part of the railway. This is Wimbledon signal box. Wimbledon in southwest London. They control the routes into Waterloo Station. Waterloo Station is very, very large. It's 24 platforms, one of the largest and busiest in the country. And this is what a signaller sees when they're trying to route trains into the station. And here you see, again, a diagrammatic representation of the railway, which is very different from what's out there on the track. If you were looking at this on a map or on Google Earth, the route doesn't look anything like this. But rather than trying to give a real life representation of the network, we use schematics, we use diagrams to show how nodes, little, the points and switches and crossings are joined together with straight lines, a bit like the tube map. Those of you know the London tube map. So we use representations of the system, and then the signaller presses buttons to tell the system where they want the train to go, and then the signaling will then set the routes and where you get those switches and crossings. You get things moving on the track so that the train can move through junctions and be routed into platforms. It's still quite manually intensive, but that's what a signaller sees. That's what a signaller works with at Waterloo. Different locations have different systems. Some are computer based, but this just shows you how we schematically represent the railway, and this is how a signaller interacts with that to manage the train service, pushing buttons to direct trains across different parts of the network. I put this up just again because this is all around how you represent data. And I'm not going to ask you to try and understand all of it. But one of our challenges, because we've got thousands of trains running around the system every day, on a normal weekday, there's about 24,000 trains running across the UK rail system. And we're measuring thousands of variables about them. And these graphs, the very top one, for example, shows how long a train takes to get through a section. It shows the signal aspect the driver sees on each day. It shows the speed of the train. It shows whether it's running early or late. And the bottom bit is showing the interval between trains. And the reason I put this up is not because it's, I'm expecting you to be able to read it, understand it, but it's more about the case of representing data is really difficult. So when you do your graphs around, I don't know, how people get to school each day, and you're drawing your bar charts or you're drawing your line graphs or even pie charts, how you represent information so that other people can understand it is very challenging. And as we enter a world of big data, you end up finding it harder and harder to be able to share your results with people. And therefore, one of the challenges I have is how do you then take a very, very large set of outputs and data and make it usable by people? And it's not straightforward. In fact, in some universities, there are departments dedicated to doing visual representation of problems. And this is just an example of how many variables you can put in a graph to try and show people what the problem is. Not straightforward, but one of the key things is if you can't share your results with people about the data and the maths you're working with, then you're not succeeding. And so the representation is absolutely key. I do a lot of work with simulation. I do a lot of work on simulating the railway system and trying to see how performance changes as different problems happen. We use very powerful computers, we use very powerful simulation. I think it's important, though, to say that simulation and reality aren't the same thing. It's very easy to get carried away and say, because the computer ran a simulation of the train service, that somehow you've got the right answer. Computers simulate the variables you put in there. Since we can't put every variable in there, it is a model. And we have to try and make the model as accurate as possible, but you cannot predict the future using them. So yes, we run some really fascinating simulators and really interesting modeling of the railway, but we always have to bear in mind that the computers don't predict the future. And that's one of our challenges. How can we accurately try and represent things without deceiving ourselves that somehow we understand what the future is going to bring us? Very, very difficult, but then all statistics suffers from that problem. Very lastly, I put this up just to show some of the other work I'm working on, which is around weather. And what this graph shows on the left is the 30 different weather patterns the UK gets. If you look carefully, these are known as synoptic graphs that meteorologists use to describe weather patterns across the country. At the center of each one, I'm hoping you can see a little map of the United Kingdom. And then what you see are red and blue representing different types of weather pattern, high pressure and low pressure. High pressure typically being associated with nice sunny weather, low pressure typically associated with winds, rain, and not very nice weather. But what we are using this to do is try and understand how it's linked to earthworks. The railway is very old. It runs across very old earthworks, and we know that if we get too much rain, you get the earth moving. And what you're seeing on the right is a map of where there have been historical earthworks movement. And what we're doing is using statistics and very powerful computing with a Met Office to understand how we can link weather to where we might have risks with earthworks moving. But again, it just shows the sheer variety of the work I do. And again, it's showing the challenges of representing data and how we use maths and statistics to try and improve the way we run the railway. So just a couple of points I want to make to you. Measurement is key. So when you think that lots of things are measured in life, yes, they are, but some of the key things aren't always. And therefore, a key part of my job is how we measure the right things. I said earlier that the maths is relatively simple. What makes it difficult is the sheer amount of it, and the fact that you have to do some quite complex relationships to say why things are causing other things to happen. We can use simulation, but it has to be matched with real life. And if it's not being matched by real life, the simulation is wrong. You can't spend your time adjusting models and then saying it's right. And I think the last point is it's everywhere, and it's every day I do maths, every day I use data, and every day I use statistics, and I really enjoy it. And I really urge you to sort of think about these sort of the interesting questions and challenges that maths can help us with. I'm going to finish with the question I opened with. Excuse me. I asked you if you coupled every single rail vehicle together, where would the front be? It would be London to York. Excuse me. London to York. That's a train of 188 miles. Sorry about that. I shall now stop sharing my screen.
Okay, thank you for that. That was really interesting. So I'd like to remind everyone, if you've got any questions, then do drop it into the Q&A facility at the bottom of the screen, and we'll both turn our cameras on so we're not just looking at a blank screen. So a question I have for you is that your role as a Director of Networks Strategy and Operation, it sounds like a big job. So what kind of things do you do in your day-to-day role?
You are right. There is quite a lot going on. So every day we're looking at how we can run the system better. And then I have projects. And one of my key projects at the moment, as I say, is working on weather and introducing systems as such. That last slide. So that graph showing all the different weather patterns is a really important piece of work I'm working on. I'm also working on how we demonstrate that we run the system better. And that involves working with the train operators to say what's the best way to get the most out of that signaling. So when I showed that earlier slide showing that green, double yellow, yellow, red, it's a very simple concept, but very hard to describe mathematically about how people respond to those signals. And therefore, I work at an industry level to say, well, how do we get the best out of this system? How do we get the best out of the complexity of running the railway? And how do we justify what we're doing? Because the railway is extremely expensive, and I don't know if people know how much one of those rail vehicles is. If you consider that a rail vehicle costs about £2 million a vehicle, and if you look at the new trains that run up and down the East Coast Main Line, for example, there are 9 of those vehicles in one train. So now immediately you've got a sheer scale of the cost of some of the things we do, and we've got to be able to justify that. So yes, my day-to-day job will be a lot around working with industry partners, saying how can we do more with this. I'm not allowed to do as much analysis as I used to, because that's what you have teams to help you with. But I always want to challenge a team, saying, can we do more analysis? Can we get more out of the data we've got? And are we using the latest technology? So I do spend, there are some really exciting parts of my job, such as working with big companies like Apple and Google to say, how are they using data? How can we work with them? So I have a huge breadth of subjects in my day-to-day calendar, working with some leading scientists, leading data providers, and just the sheer fun of working on the railway.
Mm-hmm. You mentioned just then that you approach teams, and do you think that you have to be collaborative within your role? Do you think that's an important skill that you should learn in the classroom?
Oh, very much so, because even in a company as big as Network Rail, you don't have authority to tell everybody what they can or can't do, because people have different remits and they are required to deliver different outcomes. We're trying to serve passengers because they pay for the rail fares that drive the UK rail industry. We also have customers in the form of the Department for Transport for London. And so you end up dealing with a number of people who need different outcomes, and therefore you can't say what the right answer is. This is one of the difficulties around decision making. Although maths and stats can drive you to a figure outcome, sometimes you have to interpret those numbers. And interpreting numbers takes judgment and expertise, but you can interpret them in different ways. And therefore you have to work with other people to say, how do we interpret these numbers and what are the right ones? Because it's not just about saying that there's one right answer. Well, yes, we need to improve performance, but we've also got to run the railway safely. And the railway's got to be run safely, and that might mean that you can't run performance as much as tightly as you want to, because you want to keep the system safer. So going back to the motorway analogy, there is an optimum distance between cars to keep them safe while maximizing the speed of the motorway. We have some of those same issues. So it is very difficult to say that there is one single answer. Maths helps you, guides you towards better decisions, but you can't do it by yourself. You've got to work with other people, get other perspectives to say, well, what's the right outcome?
Mm-hmm. So there's a lot of, innovation within rail. Where do you think rail will be in the next, I don't know, 5-10 years?
I would like to say further ahead than it is. The railway is a very slow moving industry in some ways because it's so big. You have to deal with different technologies all the time. So many of our computer systems are 45 years old, and there's not that much you can do with them. We still have signals on the network that are old-fashioned semaphores that were around when the steam trains were on the system. But there is new technology coming in. But one of the challenges is how you implement new technology, because you've got to get it to work with old technology, and that's remarkably hard. So it's not just a simple case, go out and buy a new computer. You've got to make it what's known as backwards compatible with what's already there. And we're not very good at it. So I do want to see more technology. I do want to see increased use of automation. We are using computers much more in computerized signaling. But if you take the Docklands Light Railway in London, which is driverless and what's known as an unattended train operation, that's quite old now. That's 30-35 years old, and we haven't seen the rollout of that across more of the UK rail system. So I think we've got real challenges in that. But it is a very traditional industry in some ways, and we need more change, and we need new thinking, new ideas all the time. And therefore, anybody thinking about it, yes, there's plenty of room for improvement.
Mm-hmm. And I'm guessing you use quite a lot of programs in your job. So is there something that you wish that you'd started to learn earlier, like let's say Excel? Is there something that you think that maybe students should be learning now to get ahead?
I do like that question. So I've got to admit, I wasn't originally a statistician. So for those of you out there thinking, well, I'm not, I don't do statistics, I don't do maths. I actually did geography, and I started out very much around what's known as human geography, which is the study of how people behave in their environments. And it was only when I started working in the railway, because transport's big in human geography, that I realized I really needed numbers to be able to describe what I was seeing. And that's when I did a statistics diploma with the Open University, which work paid for, and started learning about how you can use numbers in computers to actually to improve things. So the answer to your question is, I wish I had taken up statistics sooner. I wish I'd learned more about programming. I have learned a computer language. I use a program called R. I don't know if any of you have heard of it. And that has been hugely beneficial to what I do. And in fact, even now, I still do analysis of data because I think there are questions that are not being asked. So I will ask and answer questions myself. I just kind of wish I'd done it sooner. If I'm going to be naughty, Excel is a very good program. I would always urge anybody out there to get involved in some other programming languages, because it's only when you see what other programs are capable of, you know what the limitations are of Excel. Mm-hmm. So Excel is useful, but I would never describe it as a stats package. And when it comes to drawing really impressive graphics and visualization, then there are lots of better programs out there. So programs such as R, Python, other things, I would recommend to you. They're very brutal to learn, because it's R in particular gives you more error messages than you can ever imagine. If you get the slightest thing wrong, it absolutely beats you up for it, and you do get a bit fed up of it. But once you start seeing the outputs and you're seeing the power of it, then it does extraordinary data analysis. But there are lots of other systems out there. I just urge you to explore them, because I tell you, if you do want to do data analysis, big data analysis, Excel is not the answer. It is a useful stepping stone, but I would urge you to sort of, if you want to be curious and look at other things, do. They're free. You can download them from the internet. There's loads of help on there to how to use the best of them, and it is very rewarding when it works. It's not always the case, but it's very rewarding when it does work.
Mm-hmm. So you visualize data, don't you? So do you have to be kind of a creative person? Because sometimes looking at graphs can be a bit daunting, and I think for me personally, some of the ones that I've created have been a bit boring, and they're not eye-catching. So maybe do you think you have to be creative to succeed?
Again, I think that's a really important point. Data visualization is incredibly important, and it's actually important to remember that some people don't like graphs at all. So I showed you a graph of train planning. Some people prefer to see that as a list of numbers and timing points. and some people find that easier than graphs. So remember your audience. You remember that people have different preferences for numbers of visualization. But visualization is, in my mind, as I said, it's so important. And you can get carried away with visualization. There are people, there are whole books on the subject, and as I say, there are whole courses on it. But I do urge you to explore the capability of systems in giving you better graphics, because a powerful graph will make your life so much easier if you're trying to demonstrate to people why you've come to a decision. So if you have to justify something, graphs can make all the difference between easily or being told by somebody, no, I know better, but I've got no data to support it. So in my job, because I deal with very senior people and routes and regions and who want to know the answers, my life is a lot easier if I can show them quickly and simply the problem and how as you said, the data and graphs are key to showing people that. Sometimes it's very difficult to do it, but do try and concentrate on your answers and how you present them.
So I think at least right now there's a real push for sustainability and being more aware for the environment, like with COP26, and I know that Earth Day is approaching on the last Saturday of March at 8:30 p.m. So to try and link that with STATWARS Climate Change Challenge, and specifically, we ask students to choose 3 things in their day-to-day life that they would change to try and reduce their climate impact and carbon footprint. So 2 questions. How important is climate change to you and to rail? And what 3 things would you change in your day-to-day life?
I would say that the weather is really, really important. We've got to be very careful here about weather and future climate, but the weather affects the railway day in, day out, and it's important to understand the extremes of weather now, which can give us huge problems in safety and delivery of the service. And I would almost urge people to say, well as looking forward, you have to look back. Bizarrely enough, you have to understand how brutal the weather is. In fact, I found out a fact only very recently that I think it was 1951 where I lived, there was 42 inches of snow. And you think, I don't want 42 inches of snow because I won't be running trains. It's good for sledging for a few days, but I can tell you what, I won't be leaving the house to do that for a long time with that much snow. And we've got to remember that these things can happen, do happen, flooding, whatever. And it's really important to understand the sheer range of numbers. I'm not a good one on this because I used to work for an international company, for example, and therefore I used to fly a lot. And unfortunately, that went with the territory. I fly to North America, Hong Kong, Sweden, quite regularly. But sometimes we have to remember that there are certain things that use a lot of energy. The railway uses a vast amount of energy and always will do, even if it's electrical rather than generated from fossil fuels. We've got to remember the railway uses a huge amount of energy. When you see one of those trains moving around the network, they are using more energy than you can imagine. So if I say to you, I'm going to turn my thermostat down by 1 degree, that's absolutely nothing compared to stopping a train at a red signal and then having to restart it. So to put it into context, a fuel tank in a car, let's say, might be 50 litres. On one of the big trains leaving Paddington, one of the diesel trains leaving Paddington, if you stop it and start it again, it burns 90 litres of fuel to get back to line speed.
Wow.
So, this is an industry that is very energy intensive, and therefore one of the biggest things I can do is try and make it work as planned to minimize energy consumption. And even if whatever I do in my home or personal life, the biggest thing I can do is to get the system moving and get it to move effectively so that we don't waste energy. And I think that's the most important message I can give people, is that it's so important we don't waste energy. Where energy has value, energy has important implications, as you said. So my job, I see it as being really important, is that we don't waste any of it because it is a precious resource.
Yeah, definitely. So we're out of time. So just final question. Do you have any final advice for any of the young and budding data scientists that are watching today?
Enjoy it and be curious. I think you have to ask, look around you and say, why does something cause something else? And then how do you think, and then think about, how do I prove that? And often it will involve numbers. So just challenge yourself, look around you and ask lots of questions. And I would say that's the most important thing. Be curious, inquisitive, and the rest will follow.
Mm-hmm. Yeah. Okay, well, thank you everyone for joining us. Thank you Oliver for taking time out of your day to join us. If you want to find any more, you can go to the www.statwarscompetition.com, and that's got more information for you to find. So thank you everyone. I'll end it there. Thank you, Oliver.
Thank you.
Thank you. Bye.